So for the past few days, we've been working through packet 6. So I covered first 10 pages Tuesday, then 10 to 20, then 20 to 30. So page 30 to 60, I'm going to highlight problems. They are kind of organized. These kind of miscellaneous AP Classroom problems that are organized sequentially. So start off with limits, then moving on to derivatives, and then related rates, and then implicit, and then curve sketching, and then finally some second semester topics. Okay. So if you guys can turn to page 34, I just want to be able to run through. I'll be skipping around and highlighting certain problems. Okay, so this is number 30 on page 34. It says, which of the following statement is true? If you have a piecewise function and all your answer choices are dealing with continuity, I like to step through continuity conditions. So it kind of gives me a structure, an order of knowing how to kind of move through my problem. Okay, so the first condition is, does the point exist? So you're always going to be told in the problem, piecewise function will always tell you what the center of the problem is. So here it says the condition is around 2. So you know 2 is going to be the point that we're thinking about. So f of 2, I'll find f of 2 is 7. If you ever see this piecewise function, just know that there's a point and the graph. There's no there's not going to be separate branches of graph. This second one, yeah, the second statement is just a point, but the graph is really living with this first piecewise. Because if you say that x doesn't equal to 2, that just means this graph is everywhere except 2. So most of the graph is living with that first piecewise. The second is just a singular point, and we just want to know, is that point going to eventually fill in the hole, or will it not? So f of 2 equals 7. Second statement, does a limit exist? So limit as x approaches 2. There's no need for one-sided limit because we don't see greater than and less than in our piecewise. So just use the first piecewise function. Okay. So this one, first thing you do is you evaluate. If you get 0 over 0, you can do L'Hopital's rule. I just decided to go through factoring, but either way, if you do L'Hopital's rule, derivative, reevaluate, you're going to get a limit of 5. So your order pair is at 7, your limit is at 5. That point is not filling in the hole that's existing from statement 2. So therefore, the third condition would fail. And if you have a graph where the limit exists, but the point lives elsewhere, then we call that a removable discontinuity. Okay, number 4 is also revolving around continuity, but the statement is a little bit different. This is more of a calculator question. It says, for what values of b is the function continuous at x equals 2? So now we want to figure out what will cause continuity. So now we see that the limit is split on either side of 2, left of 2 and to the right of 2. And if we want the function to be continuous, the order pair, so we go down our conditions. F of 2 is with the first piecewise. So plug 2 in for x, I get e to the 2b. And then the second statement, so this limit exists. Now we see a one-sided limit split on either side of 2. So we'll rely on limit as x approaches 2 from the left, and then the limit as x approaches 2 from the right. So all we do is take 2 and plug into both of our piecewise, and then we get e to the 2b for one of them, and then we get 1.5 times 2 plus b. So in order for the limit to exist, these two have to be the same. So we set them equal to each other. But if you notice, this is not going to be an equation that's easy to solve by hand. So the strategy for solving an equation that is difficult with a calculator is graphing it. So I get everything over to one side, graph it, and look for the x-intercept. You can also graph these two separately and look for the intersection, but I prefer looking for x-intercept because then I don't have to go searching all around first quadrant to figure out where they intersect. I can just focus on this, following along that x-axis. So I graph it, I look for my solution, and I have two solutions, negative 2.998 and 0.647. Okay, I'm just going through and I'm going to pick out what I think is problems that are a bit more challenging, and then leave the easier ones for you guys to finish off on your own. Okay, so page 38. If you see a strange limit problem, always try plugging in your x value first. Maybe if you're expecting it to be L'Hopital's rule, don't make that assumption. Always check to see what's going on. So in this case, if we plug in 0, it does end up being 0 over 0. So that tells us there's a hole, the limit exists, we keep going, we can do L'Hopital's rule. The reason that we always want to check first is sometimes the limit already exists and we don't want to do L'Hopital's rule if our evaluation of the expression is going to give us a real number. Then we're going down the wrong process. So make sure that you're always plugging in your x value first before you decide on anything after that. Okay, so in this case, we find the derivative of the numerator and denominator separately, reevaluate. Number 12, we have a function and it's asking for what's the derivative, f prime 2, for what value of b is f prime 2 equal to 0. So we know the derivative requires us, in this case, to go through the appropriate rule, which is product rule. So we have to go through product rule. Notice that we have two separate expressions that are outside of each other and they're being multiplied. So we go through the product rule, f prime g plus f g prime, replace every x with 2, replace f prime with 2 with 0, and then now the only variable left or unknown value to look for is that b value. Take a look at page 39. This is a very common type of problem where you have a function and you have to find the appropriate derivative rule, and then you have to be able to use the graph to pull information, either order pair or slope. So see if you can try that. So page 39, number 13, is a very popular type of multiple choice question. So with this problem, we should be able to recognize, oh, to find H prime, I have to go through quotient rule, numerator denominator. So we go through quotient rule, build out all of our parts of our derivative, and then replace every x with 3. And then we can look at our graph of f and g and decide, okay, what information do I want to pull from f and g? Do I want the ordered pair or do I want the slope? So the derivative ends up being f prime of x times g of x plus 2x minus f of x plus 4 times g prime of x plus 2 all over my denominator squared. Replace every x with 3. And then on the graph of f, you're going to be pulling your order pair for f of 3. F of 3 is 4. F prime of 3 would be asking for the steepness of the graph at that point. So it's a nice linear graph here. So just pick any 2 points on this line and do rise over run. So up 1 over 2. And then g of 3 is 2. And then the slope of the g graph at 3 is negative 3. So the steepness of this line segment is down 3 over 1. And then it's just a matter of plugging in all those numbers, combining it, and trying to get it down to an answer choice that matches the correct one, 3 over 16. Like 14, also recognizing the need for the appropriate derivative rule for 14. It's going to be chain rule, nested chain rule here. So see if we can try 14. So the outside, you got that big parentheses or outer parentheses. That's the outer function there. So a parentheses squared. And then after we do that derivative, then we move on to the 1 plus f of 3x. And then we got to handle that f of 3x as well. So outside first. 2 parentheses to the first power. Replace, don't change anything with the original set of parentheses. So we're not ready for this derivative just yet. Times, now we're ready for the inside portion. 1 becomes 0. F of 3x becomes f prime of 3x. And then finally, the derivative for f of u is f prime of u times u prime. Answer choice D. Page 41, 17. Okay, so that d2y over dx2, that's the notation for second derivative. So we'll find y prime. And then after that, we'll probably get to y double prime. Oh, sorry, d4y over dx4. That's the fourth derivative. So Okay, so 2 is coefficient, that's going to stay. Natural log of u becomes u prime over u. Natural log of x becomes 1 over x. So 2 times 1 over x, or 2 over x. But if I want to get myself ready for my second derivative, I can leave it in this form and go through quotient rule, but I find it easier to just bring it up and get it ready for power rule instead. So that's my y prime. It does seem daunting to find the fourth derivative, but the nice thing is that this is power rule, so we can just keep going through power rule multiple times, and eventually we can make our way to the fourth derivative. Page 42. Oh, answer choice B. Okay, page 42, number 19. It says, let f be a differentiable function with f of 0 equals -4 and f of 10 equals 11. Which of the following statement is true about function from between 0 and 18? We see all these notations of IVT or mean value theorem, extreme value theorem. So the idea is that, well, if I have two ordered pairs and the graph is smooth, then I know that whatever lives between those two endpoints will have to be, well, it's true that we could do IVT with that information, but based off of, if you look at option D says f prime of 5 equals 1.5. So it's trying to guarantee a slope of 1.5 off the original function. And that's not what IVT does, right? IVT is telling us that if I have a low value of -4 and a high value of 11, I must be able to hit every y value between -4 and 11 at least once. This is probably more of a mean value theorem statement. The idea that, okay, if I have two ordered pairs, then whatever slope I can draw between those 2 points, I can guarantee that there's going to be an exact slope that matches what I see there. So we don't have to draw this out, but John, I'll show you real quick. If I have an ordered pair 0, -4, and 10, 11. Okay. If the graph goes through those 2 points, then whatever slope I can draw between those 2 points, let's say that slope is like a 5 or 6 or 7, then there must be a steepness that is also the same as what I drew between those 2 endpoints. Okay, so that's more mean value theorem, where the instantaneous rate of change, the derivative, is equal to the average rate of change, which is the slope between endpoints. So the formula for mean value theorem is basically saying, take the derivative, take the slope between the endpoints, set them equal to each other, and then we can find the location where the graph is going to exhibit that specific slope that we can see between the two endpoints. So that's going to match C the best.
I did the, or how do you know it's A? I did like the opposite way.
Yeah, if you do it the opposite way, then you would get let's see, what did you get?
Or I got like, because I got
Yeah, I mean, if you got the order flipped around, it should still look similar to that. Maybe it'll be
Oh.
11 minus -4 over 10 minus, oh, sorry. Yeah, which is fine. Yeah, if you did -4 minus 11 over 0 minus 10, if you work that out, it'll end up being the same number as
Yeah.
this. Yeah, so you're still right. Okay, page 43. That's right. Let me go to 44 here. Number 23. A bunch of statements about line tangent to the curve is horizontal, line tangent to the curve is vertical. So there's all these mentions of tangent, line, slope. You know it's got to be derivative related. So we have to spend the time to actually find the derivative. So if you look at this equation, offensive y's mixed into the equation, we got to go through implicits. So we'll do implicits, get our derivative to show up, and then horizontal vertical tangent. This is where we look at either the numerator or the denominator of the derivative. Okay. So horizontal tangent is where the numerator of the derivative is equal to 0. Vertical tangent is where the denominator of the derivative is equal to 0. Okay, let's see if we can build out our derivative using implicit. Okay, so after we find our derivative, we have a couple of UIDXs showing up. So let's add and subtract in a way that our UIDX terms can sit together on the same side. And then we can factor that UIDX out, divide over, and then we can get our derivative 12 minus 3x squared over 2y plus 6. So horizontal tangent is where we set the numerator equal to 0 of the derivative. So if I set that 12 minus 3x squared equal to 0, I can factor, and get 3 times 2 minus x times 2 plus x, set that equal to 0. And if I solve for x, I get 2 and -2. And the first statement is at a point where x equals -2, there's a line tangent where it's horizontal. So if I were to plug -2 in for this, I'm going to get 0. So -2 does cause the numerator to be 0, which means that at -2, there's a place where the slope of the curve is going to be 0.
So the top's horizontal. And the
That's right. Top is horizontal and bottom is vertical. Yeah, so maybe just think alphabetical. Right? Top is horizontal, bottom is vertical tangent. So if I set the denominator equal to 0, if I solve for y, I'll get y equals -8, and that matches statement 2. And if I plug -1, 1 into my dy dx, I'll get 1/2. So that's also true. So all 3 statements pass.
You have to like separate it,
Uh,
like all the way to 3. Or can I just plug it?
no,
in?
yeah, that's true. You don't have to. You could just, if you stop here, and if you plug in -2 and -8, you'd be able to get to your answer. You confirm that
Oh.
that equals 0.
You just have to wait for it. You just have to get it to equal 0.
Yes, yeah. But let's say the problem said instead, find the horizontal tangent, then you would have to get all the way to here and then set every part equal to 0.
Because there could be multiple.
Okay. Yeah, this case, they're telling you what the potential horizontal vertical asymptote is. So you could stop here and just plug in and confirm that the top is 0 and the bottom is 0 with these numbers. That'll be fine too. see. Okay, 24. It's a bit more challenging here, but it is a calculator question. 24 says the derivative of a function a is given as a prime. So we have our derivative given, and a of 1.2 equals 7.5. If the linear approximation to a of t at t equals 1.2 is used to estimate a of t, what value is their linear approximation? Does the linear approximation estimate a of t equals 15? Okay, so this one is a little bit strange because it's not a straightforward linear approximation problem, but it's still going to go through the process. We're still going to just gather information that we normally would with linear approximation. We'll find our ordered pair, we'll find our slope, point slope form, and then we'll plug in the decimal value. Okay, so first things first, my ordered pair is 1.2, 7.5. My slope a prime of 1.2. And I already have the derivative, so I don't have to do math 8. I can just plug that 1.2 directly into my derivative function. So 1.2 in for the t, so make it 9e to the 0.4 sine of 1.2. That's going to give me 15.066. Okay, so there's my ordered pair, there's my slope. Let me build my tangent line equation. Now, my variable is a little bit different here. Instead of x, they use t, so I'm just going to adapt it. Y minus y sub 1 equals m times t minus t sub 1. Now, typically, they give us a decimal value to plug in so that we can find our linear approximation value. But this problem is a little bit, it just swapped it a little bit, where they tell us, okay, we want the approximation to be this number, work backwards and figure out what the t value is. So we'll just plug 15 in for y instead, and then just have to algebraically and numerically, sorry, this is plus 7.5, not equal 7. So I'll replace y with 15. I'm just working backwards to figure out what the decimal value is from here. So we'll subtract 7.5, divide by 15.066, add 1.2. Divide by 15.066. Okay, page 45. The graph of f is shown. Which of the following could be the graph of f double prime? So this graph is very gradual here. So we do see a relative max, right? Let's imagine that relative max to be slightly to the left of 1. Okay, let me say it's like 0.8. Okay. So if this is the original graph, this is what my f prime sign line could look like. Oh, I'm sorry. They're asking for the graph of y double prime. Okay, so all I need is to build my second derivative sign line. So my second derivative sign line is where my points of inflection is. Now, if you look, it's very gradual, but do you see a point of inflection somewhere here? This is concave down, but then it changes eventually to concave up, right? Maybe somewhere here. Let me call this point A. There's a place where there's a very not easy to spot, but you can kind of tell that there's a change in curvature somewhere here, right? This is a concave down, is a slight change to concave up. So let me say at point A, there is point of inflection. And to the left, concave down, and to the right, concave up, slightly to the right of 1. So here's my second derivative sign line and my second derivative graph. I know that to the left, to the right of 1 is going to be where my point of inflection is. I know that to the above means concave up, below means concave down. So I want my graph to do something like this, right? That's got to live below the x-axis, and then it's got to switch over to above the x-axis. Okay, I don't know exactly what the curvature could look like, but I do know that I'm going to start below and I'm going to end up above. And the only graph that that fits those scenario is answer choice C.
Wait, so why don't you like follow the concave down concave? Why wouldn't it be D?
Why wouldn't it be D? Because it's not asking for the original function graph. If it was asking for the original function graph, then maybe this would be correct. But it's asking for the second derivative graph. So second derivative graph means it's not plotting what the shape of the graph is. It's plotting the concavity of the values. So I need to have something that is above the x-axis to begin with, or sorry, below the x-axis to begin with, because all these are negative concavity values, right? It's kind of abstract, right? But like -3, -4, -5, those are all concavity values. So it needs to start below the x-axis because it needs to live here. Because it's the second derivative graph, which is
So it's kind of like the positive and negative.
right. It's like I said, the positive negative with positive slope and negative slope, and instead of positive slope, negative slope, we want concave up and concave down. So
But it still counts as like positive. Okay.
right. Yeah, it still needs to be above below. Wow. I couldn't tell by looking at the graph, you know, that's going to have this shape. So if there were multiple graphs that were below and above, then that'll be more difficult.
And then what if it asks for the first derivative? That would be positive, negative still, but like.
Yeah, that's a good point. Right. So if it's asking for f prime, then it would be a little bit different. Then I'm looking for positive slope versus negative slope, and then my positive slope would be maybe slightly to the left of 0.8, and there'll be negative slope all the way down. So let's say this is 0.8, so it would look more like that. It'll start off positive slope above the x-axis, hit a relative max, and then it's going to end up below. So it'll start above and below. Then it maybe look more like this. Okay, 27. I want us to be able to look at a problem and be able to recognize when there's a need for related rates. So number 27 says a rectangle has width W inches and height H inches, where W is twice the height. So I'm going to create that relationship there. W equals twice the height. Both W and H are functions of T, so that should indicate anytime I have C time, it's possible that it could be a related rates problem here. A represents the area of the rectangle. So area of a rectangle is width times height. But I want the whole thing in terms of height, so I can replace W with 2H. So A is equal to 2H times H. So A is equal to 2H squared. Right? So now if I'm starting from this stage, then to find the derivative, I'm going to go through power rule for both sides and then make sure I include dA dt and dH dt because of related rates. So A becomes dA dt, 2H squared becomes 4H, and we're asking for H's derivative, so we need dH dt. Okay, you skip to, this is page 47. Down to number 30, moving on to anti-differentiation. Let the function defined by g of x be given as integral. At what value does g attain relative max? Now, relative max, you know, it has to come from f prime, or sorry, derivative, so g prime. So let's build g prime. G prime, if my function is integral, then the derivative of this will wipe out the integral. I'm just left with this expression, right? So let me build out g prime using second theorem. G prime is a derivative of this mess. You know, derivative integral will cancel out. This calculator, yeah. So then I have g prime is equal to -1/2 plus cosine of t cubed plus 2t. Normally, I would replace all the xt's with x, and then make sure, I know this is not going to seem like a big deal, but you also make sure you multiply by the upper bound's derivative. So in this case, ×1 is not going to impact the problem, but if this is more than the x, we got to make sure you do times the derivative of that upper bound. So what if we just graph a g prime in our calculator, and then we can create our sine line to see where that relative max is. Okay, so in our calculator, this is what my g prime looks like. Something like this. Okay, I'm just saving time and just showing you if we were to plug in the calculators, what it would look like. Now, I want to look for relative max. So relative max is where my graph is going to change from a positive slope to a negative slope. So it's going to be this point that I'm looking for, right? Positive slope followed by negative slope will be where my relative max is. So if I find this x-intercept, if I create my slope sine line, I should be able to convince myself I'm looking at the location of a relative max. Page 49. 33. Select the values of twice difference function is given. What is the value of g prime of cosine of squared 2gx plus 1 dx? Okay. This is not something that we can enter into the calculator initially, but maybe we can go through, right? Anytime we see an integral problem that's really messy and difficult, our strategy is how can I use substitution? So first thing I would do is rewrite this problem. Remember, we talked about how anytime you see a trig function where that shorthand form is written, that where else can I put that exponent? Make it what? Put it outside. And the reason that it's helpful, putting that outside, then it's a lot easier for us to identify, oh, wait, that's my u value. And then I will go through u substitution and see where that takes me. Okay, so my u value is cosine of 2g of x plus 1. Okay, du dx. Oh, wait, I think I did a little too much. My bad. Yes, we can play the calculator, but not yet, not at this stage. You're right. This is a calculator question, so we can actually handle problems that we normally can't handle. Let me try again. My u value, that cosine 2x is too much because my derivative then won't be able to match that g prime. So that's a little too much. It's going to be a little bit smaller. It's just going to be that 2gx plus 1. So my derivative is going to be 2g prime. And that's a better fit because I need something to pair up with that g prime. Okay, so here's my integral from 0 to 3 g prime times cosine of u squared times du over 2g prime of x. Okay, my g primes cancel out. I have a leftover 1/2 integral cosine of u squared. Now, there's one more thing that needs to be done is that if we are going to do conversion here, and we want to leave it in terms of u, where we can plug in the calculator, we want our bounds to also be in terms of u. So we got to take the time to convert our bounds. So we can take 0, plug it into our 2g of x plus 1, and that's what the table is for. The table is for us to make that conversion. So 2 times g of 0 is going to be 5. 5 plus 1 is going to be 11. And then my upper bound was 3. I plug it into 2g of 3 plus 1. I get a upper bound of -3. So I go from 11 to -3. Now I can enter all this in the calculator, pretend like u is just an x, and I'll do math 9, 1/2 integral from 11 to -3, parentheses cosine of x, parentheses squared, and then the calculator can handle the rest for us. A lot of the remaining pages are involving differential equations, and I feel like we've done a lot of practice with that. So having to separate variables, cross multiply, identify the appropriate integral rules, whether it's power rule, natural log, or use substitution. I think those would be good practice. And then just miscellaneous problems for the rest of the packet.
Is the calculator, do you have to switch the bounds from like just -3's at the top?
Yeah, I wouldn't, but if you wanted to, you could.
Because the calculator can do it.
Yes, and also, right, and also, we can always leave the bounds where they are. But if you want to flip it, just make sure you pull a negative outside. The only reason I would flip the balance is if I'm trying to read the graph, from left to right. Otherwise, if it's just an integral problem, I'm not going to switch the balance. You can, but that's really up to you. Okay. If you haven't shown me pages for packet 5, I can come around and check that. Otherwise, I just want to kind of give you, if you weren't here yesterday, I have these additional tests. This is a practice test from College Board. It's like 2016 international version. I have the effort, multiple choice, and the solution key. On Sunday, I'll have a help session on Teams. I'll send out a link through Remind Sunday nights, and I'll do a help session from 7:30 to 9. And then I'll also record that session and put it on my website under Sunday's date if you want to check it out after this session. All right, let me sit around and check to see if I have anything to show me. And then if you're a senior, you can turn in your packet 6 to me now, or you can wait till Monday to turn it in.
Yeah.
And we have 45. That's for you show.
Yeah, actually, that's true. Like the first one,
Sure.
yeah, thanks.
Do you recommend still going over this? Like doing the whole practice kind of?
Yeah, I think that's what I'm gonna go over on Sunday.
Okay.
Yeah. Okay, have you heard that? Sounds good.
So like. Some things.
Okay, sure. Yes. They can show me. Yeah, that's fine. Yeah, show me.
See, and what's the
Yes, I can 6. Okay, yes, show us. Okay. Great. Thank you. Yeah, great. Thank you.
I'm sorry.
So they said to be there by 7:45. You're gonna be in the Ox gym for Monday. Seven.
I did like one thing.
Okay, I'll give you.
Hey. That's what it's always like. Yeah, I'll show you the, I'll just, give you the back.
Sure. Yeah, thank you.
Yeah. What you say before the exam, you're gonna help us? I'm sorry, you say before the exam, you're gonna.
Yeah, so on Sunday, I'll do 7:30 to 9. I'll send out the remind. A Teams link to remind at 7 p.m.
Okay.
Yeah, but if you can't make it, I'll also record it on my
Okay.
website.
Are you still gonna do one Monday morning too?
I'll be available Monday morning, 7:15, 7:45. So if you have any last minute questions, you can always come by.
Okay. It's like a joint one, right? It's for both.
Yeah, A, B, and BC are gonna, they're gonna ask questions.
I might be able to do an after school